All right, welcome to, I believe, Recitation 6. I think I counted correctly, on RNN Basics. For those of you who aren't familiar with recurrent neural networks so far, this will be an overview. If you've seen them before, some of it might not be new, but that's okay. So RNNs work with sequential data, just similar to convolutional nets, where they might like scan through a data. However, the difference is that they take into account the sequential dependence of the data. So sequential dependence is when the outcome or the label or whatever you're modeling depends on previous or next steps, adjacent or further along. So one of the things that you can think of is like if you're coming up with song lyrics. I don't know if everyone knows these songs, but most of us probably do. The first task would be something like finish this lyric, and so that could be like never going to give you up, never going to let you, and then blank. So if you have a model doing that, it can be very helpful to know that last word based on the context from the words previous, which is let you down. And so the last word is down. And then fill in the blank would be also a similar thing. However, certain RNNs can also take into account things that are before the current blank in that sequence. And so you can have two different directions in the sequence going. And whether or not you use both directions is dependent on the problem. If you're trying to do something like text generation, where you're continually yes, this is being recorded, by the way. It should have said that this is being recorded, and I believe I see the recording button. So, but where was I? Oh yeah, so when you use the multi-directional RNNs or variants will depend on the problem, and so that will be discussed more through lecture and things like that. But basically, if you don't have future knowledge, like if you're trying to generate text and you don't know what might be said later, you shouldn't be using a bidirectional RNN because you can only really know what's in the past. Another thing that might have sequential dependence, but might not be generation or prediction of a next word. It might just be taking this current sound and mapping it to a letter or the word now. Could be something like, what is this word? And we sound it out and it says hello world, right? And that one's interesting because the current, we'll discuss this more, but the current input maps to a current output as opposed to the previous input maps to the current output. And so, other things like that you've been doing is speech transcription, where you're mapping speech data to letters, words, sounds, phonemes. You can also do, as we discussed, text generation and other tasks. So let's talk about the data types. There's many different ways of modeling, and my face is in the way of part of this already. There's many different types of data. One-to-one would be something like what we did for homework 1, part 2, where you have your current time step mapping to exactly a single sound or phoneme or letter, anything. And so that's sort of like what we did for homework 1, part 2. One-to-many would be like you can kick off a sentence and then it continues to generate afterwards. Many-to-one would be like text prediction on that first task that we said finish this lyric, where it would take in some part of the sentence and come up with that last word. Many-to-many would be like if you continue to generate text even beyond that. And then there's another kind of many-to-many, which is just like a one-to-one correspondence with the input and the output. And that could be like transcription or something. So what is a recurrent neural network? A recurrent neural network, I believe you guys can see my mouse. Let me know if I'm wrong. But a recurrent neural network has a connection back to itself for the next time step. So every time it goes through, it takes into account the input from the previous time step, and it has this cyclic nature here. And so that has certain properties that we'll continue to discuss. It differs from a CNN because it does have that input from the previous step or the next, depending on which direction you're going. And so it considers sequential dependence. There are variants of the recurrent neural networks that try to address certain issues that can come about when you have this recurrent structure. They're not those problems are not necessarily unique to recurrent neural networks. It's just that they're one of the networks that can suffer from certain problems, which I'll talk at the very end about. So a little meme, they remember things. It's kind of the special part of the recurrent neural network. Their hidden state is used later. Now, I have a different representation of how these look. Seems someone accidentally drew. I'll clear that out. I have a different representation with how these things look. One of the confusing things here is that it might look like there's two separate outputs here and here. These are often in most architectures that actually they're the same output. It's not doing two different things. It's just that the hidden state, HT, is the output of the layer that is also passed back into itself. And so often they'll represent it in the way that you'll see in the next slide. So this is sort of what it looks like over time as we iterate through. And I'll try to be more clear with what's going on with that output than the previous imagery. This is, so you would take in the first input and you would get out the first output. The reason why I did a 0 here and a 1 for the H1 is because certain problems will have, say, a start of sentence tag or something if you're trying to generate sentences, for example, and you would never generate that start of sentence tag. You would only be generating the first word. I wanted to just point out that sometimes there's an initial input for that. And so this is just how I'm denoting it. You might see it where there's an X0, H0 as well. And that often is used for something like if the current input corresponds to this current output. But for the example, I'm going to say something like, this could be the first word of a sentence or the start of sentence tag, and then the next word is following. So the output is the next in the iteration. That output is then passed over to the same cell. Now, one thing I want to point out is this is the same cell, but in the next time step. So the unrolled version of RNN is not any different. It's just another way of drawing it so that you can see what's going on through time. And the reason why this is helpful is to see the dependence of the outputs with respect to the previous inputs, as well as you can kind of track where the gradients are going. So the hidden state, which is the output of the current RNN, is passed into the next one. It produces its output, and so that you can still see the off by 1 here. That is because it's generating the next item in the sequence or something like that. And this will continue up until you want to stop. Now, one thing that's missing here is, and I'm wondering if any of you notice, and I'm not sure if you do, but the first iteration, is there anything that anyone notices that's different from the previous or from the next ones that are following?
There's no input from previous layers?
Correct. So there's no input from the previous layer. That means that so it still needs some sort of input. When you use something like PyTorch, they have a default that they'll give it. But I just wanted to point out that this still needs to be taken care of. Luckily, with the frameworks that you have, it will usually be given to you. But in certain ones, you might have to do this yourself. What this is initialized as, it's sort of like a weight initialization problem as well, where you could just set them all to some random numbers. You could set them to zeros, and it sort of depends on your experimentation. What is a good initialization for this first hidden state? Often people will set it to zeros if it's something like, this is a start of sentence tag, so there's nothing important about the first hidden state, so they just set it to zeros, and that seems to work fine for most people in the homeworks. But there might be a time where you have to consider what this is to improve performance. The other thing I wanted to mention was these boxes here, they don't necessarily have to be only a single cell. They can be many neurons. And so you can have actually multiple layers here that are just kind of pointing to themselves, but it's easier to think about it as a single cell for now. So I just draw it as a single box. This is another way of writing it. And this, like I said, there's an X0 corresponding to an H0. It's just another convention of how to do it, but it also makes a lot more intuitive sense when there's a one, when the first input corresponds to the first output rather than something shifted by 1, which is the next. And we'll do an example of that. And also, like I said, this makes it look like there's two different outputs, but it's usually that the hidden state from that cell is going on. And so I just like this image because it equated the two unrolled version and the normal, the normal, what it really looks like and how it works. So really quickly, before we go into the examples, in case this wasn't discussed before, I don't think it is in any of the previous recitations. I'm not sure it was in lecture. So I just wanted to make sure there's some background because I feel like there would be questions on this. Because I'm going to give text generation questions, or I'm going to, or examples, or I'm going to discuss it in that way. And I don't want people to be sitting there like, how do you, represent text to a neural network? I want that question to just be preemptively answered. So I'm going to just address it now. There's many ways of how to handle this and encode it so that a neural network can read it, because obviously you don't really pass it literal strings, you pass it in float, integer, double number values. And so because it has to be able to do math with that. And yeah, you can maybe say, oh, we can encode it as ASCII or whatever, and that's up to you. But one of the ways that they do it is you can create something like a dictionary, which is your all of the words that are possible that you could have. And then you can say, well, let's give an index to every word in it. And so let's just say that it's in order here of the words that we encounter. So never gonna give you up. That's 1, 2, 3, 4, 5. Oh, I miscounted. 1, 2, 3, 4, 5. Yeah, it used to be going to, and so it used to be n equals 6. My apologies. I changed it to gonna to be more fitting for the song itself and how they say it. But basically, let's say that never was this first word. There is a 1 here saying that I am this first word. And so you can represent it as it's one hot encoding, which is what it's called. 1 for the value 1, right? And so one of the issues with this is that you can imagine the space that this thing occupies. If this is a vector in some sort of space, you have well, it should be 5, right? A 5-dimensional, so here I can just annotate it just to make it clear because of the mistake. You have a 5-dimensional vector, right, which is a 5-dimensional space for 5 words. But see, the space will increase linearly with the number of words that with the unique words that you encounter. This can get very inefficient. You make very sparse information. It's really big. The input to the neural network might have to be really big with a lot of useless information. And so another way of doing it is you can encode it as some sort of integer or something like that. Or what you can use is something which is a word embedding. Now, word embeddings can take you can do it in many ways, but basically the word embedding is when you take the simple way of saying it is there's some matrix that operates on something like this, or the integer value, which could be just equal to 0, right? And it will operate on that and transform it into some denser vector of some reduced dimensionality. Now, why is that at all interesting? That's interesting because 1, it's efficient for the space representation, right? But 2, because of the locations in that space, you can have things that have relationships with each other. For example, if you have hot and cold, and hot is up here, you might be able to have cold as an opposite on one of the axes. Now, why is it not on the opposite side over here? And the reason why might be because this axis, this x-axis here, is a different semantic axis. And so what you see here on the right is images from GLOVE, which is from Stanford, I believe. And GLOVE is an embedding system that takes these words and creates vectors out of them in some space. What you'll notice is that the relationship between man and woman in English is similar to the relationship between uncle and aunt relative to each other, right? Where here in this space, and just keep in mind that this is a many-dimensional space. This is not actually just 2 dimensions. It's just projected onto 2 dimensions. But you'll notice that things like man and woman, sir and madam, these what is it, pronouns, nouns, they have a similar relationship to each other as they should, because one word is used more with its corresponding whatever. It's not quite opposite, I guess, but it's corresponding opposite, and their relationship should be similar. And so that's really cool that this system And keep in mind that this wasn't using people telling it this is how it should work. This was using some sort of fitting method or embedder that learned how to represent these words. And so this also happens here, as you can see: slow, slower, slowest; short, shorter, shortest; strong, stronger, strongest. So this is a really cool way of trying to represent meaning and relative meaning with words, and have them kind of carry more information into the network and have it be able to use that. And so one thing I wanted to mention was, when you output this stuff, you're going to output some word, right? But it's not really a word that the network produces, right? Does anyone know? I guess I kind of just say it here. What it actually produces is some numbers. Now we want those numbers to represent the probability of that next word. And so we can say, let's say we have never going to give you up, right? We're going to have it try to guess this upward. So imagine it's not there. I have tried to highlight it. If anyone is colorblind, I'm sorry, it's in red, but I hope that it's grayer on the grayscale. So yeah, this is n equals 5. So there should be a probability distribution with a vector. I didn't want that thing to disappear. But anyways, a vector where this 5 vector, where each index is the value probability of that word showing up. So at the end of the sentence, you would want the probabilities to be weighted heavily on the last word. So yeah, okay, these words might exist after you, but we want up to be the highest probability because that's the word that was supposed to be predicted there. And so as you can see, this probability distribution is sort of doing that. It's just an example, obviously. And they should sum to 1 as well, which is why often a linear layer might not output something that sums to 1. So often people will use something like a softmax, but that's sort of just a choice, because you could also try to put the stress on the linear layers to, or some other kind of layers, RNNs or anything, to learn the softmax on its own, but that's a choice to make. Another example would be, the same thing, trying to create that sequence. However, in this case, you'll notice that when it's trying to predict down, there's 2 possible words it could be predicting here. I'm sorry, I'm trying not to move my pointer so that thing doesn't show up on the bottom left, because I believe you guys can see that. But as you can see, there's 2 possible words it could be producing based on this data that we have so far, because it says never going to give you up or never going to let you down. And so it could be either up or down. And so what you can sometimes have is an equal probability between the 2, because if it only remembered, the previous n steps, say like 2 or 3, it's going to say let you down. You might not know the difference. Or if it only remembers the last 1 step, it'll say after you, it's either up or down. And so, but if it remembers further back, it might remember let and give. And so then it would say, oh, this is a chance when I use up with corresponding to give from 2 previous. And if it's let 2 previous, then I'll use down. And so that might be an example of where the probabilities would be shifted. That memory does play a role in how far back it can go. So I just want to go through a quick prediction example. This is some sort of embedding or encoding of never. Oh, one moment. Before I move on, there was a question. So if x0 is the first word in the sentence, the output is h0. And if x0 is starting tag, the output is h1. Is that correct? That is not, it's not about whether or not x0 is the starting tag of the first word. It's about whether or not you're predicting the first, something that has to do with the first input corresponding with the first output. An example of that would be speech transcription. You hear some sound, and that first sound in that time step should correspond to the first word or the first phoneme in that speech data, right? But in something like text generation, where I'm trying to come up with the next word, and I take input from, I take in the first start of sentence tag or the first word, doesn't matter. The point is that you're not producing the same word in that same time step. You're producing the next thing, the next part of the phrase or the sentence. Did that answer your question, Fan? if you have a follow-up, go ahead and shoot in the chat. And I will keep going because I don't see you chatting yet. All right. So let's go through a prediction example. Let's say that you know that you have this phrase and you're going to pass it this phrase. And I just put in gray below it just so you can see. Okay, great. Great, I answered the question. All right. So let's say that I have the phrase below just so you know the whole phrase. I'm sure that many of you do, but just in case, we're going to predict up. Okay. So we're going to give it some initialized hidden state that can be zeros. We'll give it some encoding of never, which is, you know, embedding or something. And one little thing to point out is that PyTorch actually has an embedding layer that you can call to embed things. So if you do have an integer value for a word or something, just check what that takes into as an input, just to be on the safe side. I believe it takes actually integers rather than one-hot encodings, but I could be wrong. I just don't remember off the top of my head. So never is going to produce some hidden state, which is equal to the probability of the first output, because this is the 0th input, right? The first output with respect to, or given this initialized hidden state and the word never. Now, because we already have going here, we can pass this hidden state, but we can also give it going. And so we give it the ground truth here of the next word, and then it will also output the second hidden state, and that is the probability of word 2 given that first hidden state and going. And what you'll notice is that these hidden states are some combination or calculation that aggregates the information from the previous time steps, right? However, that full information is starting to be combined. So the percentage of say the first input or the 0th input and this output here, this hidden state, as it goes through, might start to diminish as you try to remember more and more things. And that's just a nature of when you pack things into a finite vector or a finite amount of space for information, you don't have infinite space to hold that information. So there's certain things that can happen because of that. Like it will start to diminish the much earlier time steps way back in the future, which is what I was referring to when I was saying, you know, whether or not the network will consider give or let from the two previous words. If it can't remember anything beyond you from previous steps, then it might say up or down. It won't know what to put in the final step. And so we get through all the way, the sequence, and so that way it has the full hidden state, and it will produce a probability of word 5, which is hopefully going to max out, or the max of that, or the highest probability should be the word up in that index. Are there any questions on that? Just let me know, and I'll answer that. I think that one is a little easier. The next example, it gets a little more, it can be a little more confusing, so there's a caveat to it. All right, no questions so far. Oh, so is H5 is up? Okay, so H5 is not the word up. It is a probability distribution. So remember I said the output is a probability distribution where each index corresponds to some word. Now, if you're, this is only if you're trying to predict words, by the way. If you're trying to predict letters, or, you know, in Japanese, they have kanji, like the written characters that are like the Chinese adopted characters, or like in Chinese where you have like characters, you don't have necessarily words, and sometimes you can have a combination of characters that mean a word. Sometimes you want to do character level predictions or generations. And so the probability distribution could also be over characters instead, or any sort of sequential output that you're trying to produce that has, you know, that dependence. So H5 here in my example is not the word itself or an integer value. It is a vector where each index is the probability of the word at that particular index. So if never is the 0th item in the index, right? Never should be a very low probability here, where up, if it's the, you know, the 5th one, or I guess it would be the 6th here, because I didn't switch them all to gonna. My bad. I'll do that before I post it. But anyways, I clicked. But yeah, does that make sense? Did I answer your question, Austin? So it is a probability vector with up has the highest probability. Yes, after training, you would hope that it has the highest probability. Initially, when you're first starting, it might not, and so we'll discuss the problem with that in a minute. But yes, we will. You would ideally a trained network. It would be some probability vector where each index is a probability, and up should have the highest probability. It is a probability distribution of all words in the vocabulary, or can you make it a subset? So there was a question saying, is the probability distribution of all words, or is it a subset of the words? Ideally, it is all words if you want it to be able to predict every single word. If you want I haven't heard of many cases where people will use subsets. I'm sure there's somebody who has a reason why they do it. But often it would be a vector of probabilities for all of your words. Now you can imagine that the output would be massive at that point. And so that's why there are certain decisions you might make, such as, in English, there, at least there's 26 letters in the alphabet, right? So maybe using a letter level prediction might be nice because your vector output is only 26 characters or 26 possibilities if you use just, uppercase or lowercase only. And as opposed to a dictionary of all possible words, which could get into the hundreds of thousands and all that stuff. So that's up to you. But I believe that generally it is the entire pot, all of the possible outputs that you want to generate is what should be the size of that vector. Let me know if you have any questions on that. All right, I'm not seeing questions so far, so I'm going to keep going. So let's talk about a generation example. A generation example is, so when we do generation is when we try to continue the sequence as we go, where we're not going to stop, okay, at just the first prediction. So we have something, it produces its probability with respect to, or given the first word and the initialized hidden state, it's going to take in the next word, and then it's going to have this, and then it's going to pass it in. Oh, I should have hid this. I wanted to hide this. But there are a couple of ways that we can try to continue this sequence, because we've already now produced, hopefully we've produced a vector with the highest probability for the word to. And so the question would be then, oh, how do I continue? And you would hope that your network would have such a high probability on the word to and a lower probability on everything else, and be so correct in that you could take the max of this, and I guess it technically should be argmax. I believe in Torch, max produces both the value and the argmax, so it would be like max item 1, not the 0th item. But just leave that aside for now. The maximum probability item in H2, the hidden state, which should hopefully be 2, the word 2, and then you would hope that would give it enough information to then get out this next word. And so you can continue to generate this way, and you can generate more and more. But as you can see, if H2 or H3 here is slightly off, right, you can start to get this weird thing where if it gets the wrong word at those locations, it will quickly start to diverge and go off into some weird direction in the language model, where it will say the next, it will start to just put weird stuff afterwards because one of them was slightly off and the word was wrong, and might have trouble recovering back from that. So if you've ever seen, like any sort of online example of, hey, I taught a thing to generate text, and this is my, this is what it looks like. If you might have noticed that towards the end of the generation, they had really weird sentences that started to not make sense, or it started to repeat itself over and over, and found some like infinite loop of like to be, or something of very likely words. And that can happen because if those hidden states have any mistakes in them, they won't represent the language well, and then the following iterations could all be garbage. So is there a problem you could foresee when training with this. I'll give you another 10 seconds if anyone's typing right now.
I didn't quite get your question. I guess one solution could be beam searching.
Yeah, so what I'm saying, my question is, when I'm first training, when I first start. Yeah, Austin, yes, correct. So if 2 is wrong, then everything else is wrong. So and someone is so yeah, the suggestion of taking the whole probability sequence instead, then, well, that's what the hidden state being passed to it is doing, this arrow here. So the question was, what is there a problem that could arise by trying to do something like the max of this hidden state, and if that word is wrong?
Oh yeah, got it. Because it's this is basically a greedy search, so it may not be the optimal.
Yeah, and then also it will have trouble learning, because it will always, if it produces garbage here as the max at the beginning, because you're effectively on your first iteration, you're almost at random generation of stuff, right? Because your weights are initialized at random, or whatever initialization you use, And what will happen is it will have trouble learning, because it will be so wrong that the gradients will almost, they won't be passing information through. And also, it might only be learning like this first iteration. When it does, another 2 afterwards, you want it to learn from all 3. And so there's a way to handle that. There's different methods that people have come up with, but one of them that we'll talk about is teacher forcing at the end. But I just wanted to give you that vocabulary term, and I'll explain what that is in a second. But I guess I'll explain it now. What that is you can actually, while you're training, the entire phrase never going to give you up. So what you might do for the first, 1,000 iterations or some number of epochs, you might just give it all of the ground truth inputs, never going to give you. You might actually just do that because you want it to at least learn its generation to its current output, right? Or the next word, which is its current output. And then hopefully you can start to learn the recurrent sequences in the later epochs if you stop forcing the ground truth input here as the max. Some would say. Oh, interesting. I'm not sure about that. I would have to think about that. But I'm going to move on now instead of the H2, H1. You are doing, that is no longer conditional probability. That's the probability of all 3 hidden states there in your comment. Yeah, I'm not sure about that because probability of H3, well, word 3, I guess, given H2 you'd hope that H2 contains information from the previous. So is there any question on possibly just force feeding ground truth instead of max argmax of H2? That's what teacher forcing is. That's just one of the techniques that you really might want to use later on. You can also make it so a teacher forces some percentage of the time, like 90% of the time at the beginning, and often we might reduce it as we go, so you can start to learn the sequential dependence. All right, moving on. So one thing I wanted to highlight, let's go back to this slide here. There's something missing from this image that we've sort of we've seen now in those previous slides that I've shown you, but that isn't shown here. And so, for example, let's say you're predicting the next word. Is there some part of this image that is missing? Any of these blocks? I'll just say it just so for the sake of time, because I believe I'm taking a long time for this. It is that there is an output for all of these in these previous ones. So there should be blue blocks coming out of each iteration here, like the many-to-many as well. There should be 2 more blue blocks where they are outputting. The difference is that the only thing we care about is these last 3 for the many-to-many, and the many-to-one, the only one that we care about is this last one. that's just something to keep in mind, that because the hidden states are being passed, it doesn't mean that they're not outputting a hidden state as well. And so when you're training, you're actually doing a loss on all of these as well, all these non-seen outputs. But the inference is only showing the last one. This is the one we really care about. But training, you can actually do a loss on all of them. So it's sort of an interesting idea. And I just wanted to point that out, that's probably how you want to do it, because the more you can update your parameters and improve them, the better. Okay, I just wanted to go do a quick image of what backpropagation might look like and point out what happens. So basically, as you go back through, obviously, for a single cell, it will backprop through its own self, or linear layer, or whatever activations it can backprop through. But the information also has to go back from the next outputs, or the next outputs loss also has to go back through the previous. And so it's this chaining all the way through. What this is although let's say this is one cell, although this cell is an RNN that is only one layer deep here, you can see that by the time you get over here, it sort of acts like it was 4 layers deep for certain parts of the gradients, at least for this sequential dependence portion. And if that doesn't make sense to you, please put it in the chat, because I would really like to make that very clear, that what happens is because you pass these back through, it acts like it's a much deeper network for that portion of the gradients. And because that part is the sequential dependence part, that part is really important for the learning and what the RNN's value is, what makes it really powerful. This can have certain problems. It can actually happen in both directions. It simulates a really deep network all the way when you go to the output that produces loss 4. So let's talk about some of the things you can run into. After many iterations, so don't worry too much about the images. They look kind of fancy. They're not my images. But this top one is an RNN. The bottom one is the LSTM. I'll talk about why the LSTM matters here in a second. The short-term memory is something that can happen where, as these things pass through and go through an activation, the previous hidden state, if it continues to go through activations in between, because you can see the tanh here, they will, even though there's supposed to be some sort of aggregation or combination of the previous information, since tanh is only between -1 and 1, or sigmoid is only between 1 and 0, that means that, and non-inclusive on the edges, that means that the activation is always going to be something reducing the previous information by less, like some factor that is less than 1. Over many iterations, if you multiply, 0.99 to the power of something, right? Even 0.99 will start to get very small after some number of iterations. And so even if you're maintaining a lot of the information, put that in quotes, right? A lot of the information, it might not be enough because it doesn't carry all that information all the way through. And so you can end up having RNNs that only can go some like 10 steps in the future. I don't know the exact number. You can do the math yourself. You might need to in a quiz or something. But it might only be able to go so many steps before you start seeing a diminishing information from, say, the first input. That 0th input might not be remembered by the 50th output. And so that whole dependence where I was mentioning, it might only remember the previous word, you, right? You need it to remember 2 words before. This also in the backpropagation direction, the opposite, is the same thing, where the gradients might not be passing their information back through to teach about sequential dependence, because the gradient, say, for example, the derivative of tanh, it kind of looks like a bell curve right between 0 and 1, which means the gradients are going to be reduced by some factor, because they're not necessarily always going to be multiplied by 1, right? So the gradients might start to vanish and go to 0. I haven't not quite sure about exploding gradients in this case. I think it's more likely for the vanishing gradients, because the derivative of the activations that produce the hidden states are between 0 and 1. Now you have different architectures that try to take on these problems, like LSTMs and GRUs. I wanted to highlight the LSTM because there's a pretty picture here where it shows how it tries to handle it. Don't worry about all this stuff. You will learn this in lecture later on, where we'll go over the math, or professor will go over the math and teach this all to you. What I want to highlight here is this top bar, this top line that passes through all of them. And what I want you to notice is that this has few operations on it. What's happening here is that it's taking in the previous hidden state, passing it through. The current output has some sort of influence on it. Don't worry about that yet. You'll cover the math on what its influence is. But it can maintain this all the way through, kind of like a skip connection having, it's not quite an identity where your previous hidden state is passing directly through, but it is sort of like that, where you're trying to pass that information directly, and it creates sort of like a highway where your information that you want to remember will be maintained for much longer on this highway and continue forward, as well as the gradients propagating backwards. The gradients that you want to maintain will be propagated backwards. There are certain terms in here in this math that are telling the telling the network what terms to forget based on the importance of the input. So it doesn't always replace what's in this highway. There are times that it can zero out what this input is to make sure that it's not important, and it will maintain the most important parts in this hidden state highway. We've already discussed, so moving on, we've already discussed some of the issues that can happen from cold start, right? So we say teacher force, right? Where you give it, instead of the argmax of the probability distribution from the previous output in a generation task, you can also just give it the ground truth when it's first learning, so that you can force it to learn the correct things, at least for some amount of time. Often this is done in stochastic nature, where some percentage of the time they are doing this, and then that percentage can reduce over some number of epochs, so that slowly it learns better and better. If you don't, it will take an extremely long time for it to learn, because it will have to get lucky enough on the first random outputs to get the correct words in that sequence all in a row, which you can think of the likelihood of that happening, the probability of that happening, with a large vocabulary. Another issue which I haven't mentioned that can happen is this lack of exploration, where what might happen is that one of the probabilities of the words will be so high that it won't ever see whether or not another word could be used in that location. If you have, for example, that where it says never going to give you up, never going to let you down, up and down, right? If it only ever learns that up is correct because it learned it first, and it made its value, that probability, so high that it never learns down, it will never get feedback from that. And so it won't explore other possible words that are there. So one of the ways that people address this is by introducing noise into the probability distribution outputs before they're passed in to the max, that argmax part, so that the output will have the correct probability distribution, but just before, we'll add plus noise in the max term, so that you can start having it try out different things that might be almost as probable. And then finally, even with an LSTM, the early terms might still be forgotten after some number of iterations. That dependence on the very beginning or the end out of order can start to be lost in many different, all of the RNN variants can have that issue. And so depending on the problem, there might be a time to use something called an attention. This will be covered in a later recitation. So don't worry about what this is now necessarily, but I just wanted to call to your attention that that's what that was trying to address. So all these things have a reason, and they're trying to address their problems, right? The architecture differences are trying to address issues of short-term memory or vanishing gradients. And then we have various techniques for addressing training issues for things like, it's not the cold start problem, or the RNN not exploring very much. So I have at the very end just some resources for you. I'm going to stop sharing in a second if there's no questions. Joseph, you can start to get your stuff ready and take over the sharing here in a minute or in a second if there's no questions. I'll have to go back one slide.
All right,
Any questions?
sounds good.
And feel free to post it in chat while Joseph is going. If he can't get to it at the time, I will be monitoring the chat as well. I think there are no questions so far.
I'm sorry,
Okay.
I missed the teacher forcing point. I wonder what that is. Could you explain
what?
it?
What point? Sorry.
Teacher forcing.
Oh, the teacher forcing point. Let me just go back really quick to this. So you see how this is the max of the probability distribution from the previous output. If you do this, let's say when you first start out, this H2 is a random distribution. The probability of getting the correct word here, like the probability of that correct word might be very low, and it might not actually choose it first. And so what you'll have is some garbage word here it's like a random word that actually has nothing to do with the phrase. And as a result, you won't learn anything from this iteration. Not only that, but even in later epochs or later iterations of training, if one of these terms is wrong, the rest of them are thrown off because they will remember that this previous input was very wrong. And so you won't learn anything from any iteration after an incorrect input. Does that make sense?
Yeah, makes sense.
Okay, so what happens is instead, while you're first training, because you're basically getting random words, it's just guessing randomly, you can put in the ground truth, which is this light gray version below it. You can put in the entire ground truth phrase and try to force it to learn the correct things by forcing it to take in the correct inputs. And so that's like teacher forcing, right? You're being a teacher and you're forcing it to do the right thing. Any questions on that?
I see, but I wonder, isn't that how we usually train? We have the words. Let's say if it's a language generation model, we just have a bunch of sentences and then just force it through the LSTM, or any RNN.
So if you always give it the ground truth when you're training, what will the network start to focus on as the most indicative of what the next word is? This is a hard question if you haven't seen RNNs before, actually, now that I think about it.
I remember reading something like, I think, for example, for birds, when they're training, they actually drop, I think, randomly mask 10% of the words and something like that.
Okay, so that would be more like, what that's trying to do is, so it's a similar answer to what I'm actually trying to get at. So if you always give it the previous word, okay, correct, and you're trying to generate further on, what will happen is it will start to rely on that input only in this direction and not the previous hidden states. Does that make sense? Because it's always getting the previous word, and it will start to learn only how to react to the previous word and not necessarily to all the words before from the hidden states that are aggregated down the chain. Does that make sense? So it might heavily weight this input and this input more, or much significantly more, than this aggregated information from the sequential dependence. Okay. Now that's why some of the time you will want it to just guess the wrong word, or so not guess the wrong word. You will want to have it rely on the previous hidden states by not forcing the correct ground truth down its throat, right? You don't want to force it every time, because at some point you're going to want it to learn that sequential dependence. Now, you at the beginning, you might need to do more teacher forcing than you will later. Does that make sense to you? And I'll explain that BERT thing in a second. Did that make sense?
Makes sense.
Okay, so you want the sequential dependence. Let's talk about what BERT was doing there, why they trained it that way. The reason why, from my understanding, the reason why they trained it that way is similar to dropout, where you want it to learn dependencies from many different directions, right? Like many different word sequences. So sometimes words depend on 3 words before it, but not the previous one so much. And so that's like a weird jump to make, where you're saying, don't worry so much about the previous word. Worry about 3 words before you, right? But but it's hard to teach it to do that. So what they'll do is they'll drop certain words and say, try to learn this randomly drop sequence, where you want to pay attention to these other words as well. And so you can do things like by hand or randomly drop different words to try to teach it to pay attention to different relationships. And I'm sure you can think of in many languages times when a word much later relies on a word much previous to it, right? Much earlier. And so it's sort of like teaching it language and various dependencies. And so it creates this sort of like, you know, information from all aspects sort of deal. You're trying to teach it all of the relationships of all the words. Does that make sense?
I see. I see. That's
Yeah.
interesting.
That's how I
And
understand it.
yeah, not to belabor the point, but yeah, just to hammer it home, you gave the example of where they dropped 10% of words, for example. So we can see with teacher forcing, there's this one extreme where 100% of the time we feed in the ground truth. And then on the other extreme, there's where the model is doing all the predictions itself. We feed in 0 of the ground truth, except at the first time step. So there's all this in between, right? So in the example you gave, it's not 100% teacher forcing. It could be 10% teacher forcing or 80% teacher forcing. So we don't have to be giving the ground truth every time. It could just be part of the time. And during training, especially in homework 4, you'll find that you'll want to start with 100% teacher forcing. Some people call it 0% teacher forcing, but explicitly what I mean is you feed in the ground truth 100% of the time. And then you want to gradually, after each epoch, reduce the teacher forcing rate. And the more you're able to reduce the teacher forcing rate, the closer you are able to make the conditions during training time look like the conditions during inference time. Because during inference, you're not going to be able to have ground truth. So your model will be better for the less teacher forcing it has. But you want to be efficient with your training, so that's why we start with that high teacher forcing rate.
Awesome. Any other
That's
questions?
interesting. That's interesting.
No problem. Alrighty.
So
Thank you so much.
No problem.
yeah, no problem. I guess I'll just jump into the code here. So we started a little early my time. It was about 3 a.m. So I hope you can forgive me that I have my notes here. You can forgive the setup. So yeah, so basically, as is tradition, we're going to be going over some of the core components of how to do a language model for an RNN. And specifically for this problem, we're going to look at how to take a sequence of characters, we'll look at 200 characters, and then predict an output sequence of 200 characters. Specifically, for each character in the input sequence, we want to be able to predict the next character. So Kinori showed the many-to-many, one-to-one, many-to-one. So this is kind of the one-to-one case. Sorry, the many-to-one case. But really, when you're looking at the RNN, it goes from one sequence to another sequence, and yeah, so that's what we'll be going over. So yeah, and just as a little overview, when thinking about neural networks in general, there's usually 6 core steps. That's the data loading, the model definition, forward propagation, loss calculation, backward propagation, and gradient descent. And so we'll be going over those now. And the focus is primarily on the model definition because we're introducing this new model type, and PyTorch enables a lot of these components to be done using their API or automatically. So yeah, so we'll be talking quite a bit about the model. But to start, we'll just have a look at the data here. So yeah, so for the first part, the data loading, so before I go into the data loading, just to make the example, to reiterate, we'll take the first character, we'll use that to predict the second character, use that to predict the third character, use it to predict the fourth, and so on until the end of the sequence. And so, yeah, so looking at the data loader, we're going to have a sequence length of 20, and we're going to look at all the characters up to but before the 20th character, and that will be our inputs, right? Because we're starting at the first character, and then we go all the way until right before the end. And for the outputs, we start at the second character, right? Because we use the first character, predict the second character. That what is being predicted, that is where we're starting, which is, not the character after the first in the sequence. So yeah, so that's what our data set class looks like. And yeah, so for that, next we'll go into the model. And for the model, there's a few things to consider, but just starting it off, the text data it's not numerical, right? And this is a problem because neural networks require numerical data for its inputs. So we saw we could use one-hot vectors at the beginning, or even integers, but these are large. One-hot can be really large, and as integers, there's not that much, the information being represented is not ideal. So to fix this, and we discuss this a bit more in lecture, is we use an embedding to create a more rich numerical representation of the text data. And yeah, so that will, so when you're going through lecture, the question of what is an embedding is something you'll want to think about as Biksha goes over those topics. So yeah, so after we get the embedding, that will, like I said, it creates that rich numerical representation. That might sound familiar because for homework 1, part 2, and for homework 2, part 2, we had those feature-rich starting numerical representations. For homework 1, part 2, we had a spectrogram. And then for homework 2, part 2, we had the images. And for homework 1, part 2, what are we doing? We're mapping the numerical representation that is the inputs to another numerical representation, which is the logits or the output of the model. And then to make our predictions, we take the argmax of our output numerical representation, and that gives us our classes, which were phonemes. And then for the homework 2, part 2, yeah, similarly, we're mapping that numerical representation to another numerical representation and taking the argmax of those to get our classes, which happen to be persons. The reason I put it forth in this kind of repetitive kind of way is to realize that the modeling process here is very similar. And actually, you can combine the different methods at different points of the modeling process. So you can have, in homework 2, you might have had a CNN followed by a MLP. And in this case, now that we have this numerical representation, we can choose if we want to use an MLP at the beginning of our model, or a CNN at the beginning of our model, or even we can just go straight from our embedding to the next part of our modeling process, which is the LSTM. So we'll just be going straight to the LSTM. So that's why we have, yeah, we have our embedding layer, we have our LSTM layer, and yeah, those are the two core parts that we're starting with. And yeah, and then I'll talk about, yeah, I guess I can talk about right now. But yeah, just so I don't forget to mention, in the wild, the decision of what you use, whether you want to decide to use MLP or CNN or neither at any stage of the modeling process, you'll want to see what the author did. Or if you're creative, you can experiment with different things, maybe do an ablation study. But yeah, in general, for RNNs, starting with either using the embedding that you made or using a CNN is preferred because there's this kind of temporal awareness, like it's preserving the sequence. Whereas for the MLP, every input is mapped to, every node in one layer is mapped to every node of the other layer. And that can be kind of confusing for the model to learn. So yeah, those are some considerations. And yeah, so basically during forward, we pass our batch to the embedding layer. We pass the embedding to the RNN layer, and then we follow the RNN layer with an MLP. So that's another thing to realize, which is that we talked about going from a rich numerical representation to an enhanced numerical representation using MLP, or just going directly. And then after you go through the RNN, you have your outputs, and you can follow that with an MLP, a CNN, or nothing if you prefer. And the same kind of considerations are there where, yeah, whenever you map from numbers to numbers, that introduces the, yeah, that you have the option to use one of the modeling techniques that we have. So that's what we're doing here. We're going from an embedding to an RNN layer to a through a linear layer, and that linear layer is our simplified MLP. And just for reference, and you'll want to do this when you're introduced with new layers, or if anything seems unclear, is that when you look at the documentation, so I just look at the PyTorch RNN layers, and you look at the documentation, if you're ever confused on what the inputs or outputs should be, when you go in the documentation, it will say, here we can see that for RNN, the dimensions are sequence length by batch size by input size. And so that should be a sanity check for you in the code, is that if when you print the shape of the input to the RNN layer, and this is the same for the LSTM or GRU, if it doesn't follow this structure, then that might be a concern. And you may consider, if one of these is different, maybe you have batch first, so you want to make sure that you identify that as such, and you just don't want to confuse. Yeah, that's one of the first things I do with students during office hours, is go through their inputs and outputs, making sure they
Joseph,
make sense. Yeah.
can I add to that?
Sure.
I don't know if you mentioned this. I realize I might have not heard you say it, but for those of you who are new to this, there is a very strong possibility that your RNN variant, whatever it is, RNN, LSTM, can learn with those things, out of order, and it will even start to improve and almost like it will look like it's performing better and better, and then it will just plateau super hard. So please, yeah, double check those, because that will save you a lot of time in that it won't show you an error every time if you do that out of order.
Right. It could learn so if you pose the problem to the model incorrectly, it could learn to model the incorrect problem. And it might be really good at modeling the incorrect problem. And you might see your loss going down. But fundamentally, if it's the incorrect problem, it doesn't matter how much your loss goes down. Yeah, you want to be careful of that. That's a good point. Cool. So yeah, now that we understand the modeling, and the generation part is pretty similar for forward. It tells us what parts of the model we have as inputs to predict each time step of the output. So I'll go quickly to the training part. And during training, right, we see that in the, what were the steps? There was the data loading. So we get our values from the data loader. There's the model, a definition, which we just went over. There's the forward propagation. So that's pretty straightforward. You feed the inputs to the model. And then there's the loss calculation. So here, the loss calculation, for the criterion, we have cross entropy loss, right? But what makes this one special is that for the loss, what we were used to is we have like a 2D array, maybe batch size by the number of observations, right? Here we, from the RNN, from our model, we have a 3-dimensional object where it has the output dimension, the sequence length, and the batch size. So to use the loss, we want to look at, okay, what do we get for all of the time steps? We can look at that by simply looking at the for all the time steps, we can concatenate them and then look at, okay, for each time step, how does that compare to what we expected to get? And then we do that for each time step. So yeah, so when we do that, it's like a one-to-one comparison. This is our output from the model. This is our time step for comparison. We do that for each one. And that allows us to use the cross entropy loss. And yeah, which makes it a very similar modeling problem for the loss. During lecture, we'll talk about CTC loss. And in the next recitation, we'll go over how to get that set up. But yeah, the core of that is that there's like this temporal component that's not really taken into account when using the cross entropy loss. Like really every time step is kind of treated the same here. And one of the students mentioned beam search. That's also something we want to be thinking about, is that maybe greedy search is not always the best way to go. And those are things to think about in a later lecture. So yeah, now that we have the inputs that we pass to the model and that we calculate the loss, we can do backprop, and that gives us our gradients, and we use the optimizer to do gradient descent and update our weights. And yeah, so this should feel very familiar. And yeah, and for validation, it's a similar story. And cool. So we'll be sharing this recitation with you all. And it looks like I'm short on time, but we've also included, after you watch the lecture and get familiar with some of the considerations involved with different sequence lengths and some of the distributional considerations involved with that. This implementation that we have starting here is with the fixed sequence length, right? So you might want to know how to do variable sequence lengths, and we give an example of how to do that with packed sequences. If you wanted to look ahead, but yeah, that's it for this recitation. I think we're right on the dot. So thanks, everybody. Any questions for me or Kinori? All right. Well, our time is up. So thanks everybody for being here and hope you have an awesome day.